All right, well, good afternoon. So I'm Dr. Eddie Piner, a professor with the physics department and the material science engineering and commercialization program at Texas State University. Before we get started, one quick note for the audience. If you can, at the bottom of your screen, you should be able to see a Q&A button. I would encourage you to use that if you have any questions as we go along, we will try to address those in real time, or if it, whenever it makes sense to do so, we may hold it till the end. So again, just note your Q&A button. That's how you can interact and interface with us during this interview. And so with that, as a quick introduction, as the slide was indicating before, we have Dr. Tania Betancourt. She's an associate professor with the chemistry and biochemistry department at Texas State, as well as Damilola Runsewe with here at Texas State as well, obviously one of our PhD candidates, or as I affectionately call him, one of our scholars, our PhD scholars in the MSEC program. So welcome. Thank you all for joining us this afternoon.
Thank you very much.
So well, let's go ahead and jump in. So I guess to get things started, just to let's familiarize the audience with what you all do. So Dr. Betancourt, if you, in terminology that general audience can understand, because a lot of what we do is obviously highly technical here, but just share with everyone what you do, maybe weave in some of your background, how you got here, if you like. But yeah, exactly, what's the research that you conduct and direct, and maybe at a personal level, how does that relate to people's lives, on a day-to-day basis?
Of course, thank you so much, Ed. So my background is actually in engineering. I obtained my bachelor's in chemical engineering and my graduate degrees in biomedical engineering. So a lot of the work that I do is in the development of materials that can be used for medical applications, which I think a lot of our audience can relate to. My background specifically is in the use of polymeric materials, so plastics, materials that you might be familiar with in other applications. But what we do is to try to use these materials to be able to detect or diagnose or monitor or even treat diseases, especially cancer. We're doing a lot of research in the cancer area. To tell you a little bit more about the background, I got my degree from UT Austin, my graduate degrees, and I worked in industry for a little bit before coming here. And both during graduate school and in industry, I worked in this area of biomaterials. I worked a lot on the development of biosensors, the development of therapeutic nanomedicines. That's that keyword nanomedicine that some of you might have heard, and it's just a big term to describe materials that are small in scale that have therapeutic or diagnostic functions. And a little bit maybe to tie in with the big idea of intelligent materials. We're really interested in developing systems that can be activated either upon an external intervention, that could be from the doctor or from the investigator, or that can be activated by interaction with a disease-associated molecule. And that activation could be something like provide us a signal, in a biosensor case when we're trying to diagnose the patient, or it could be a function such as release of a drug at the site where it's needed, or it could be something like activation of heating to be able to undergo what we know as photothermal therapy, for example, where we're trying to kill cancer cells by heating locally without causing harm to the rest of the body. So that's kind of what we work on.
Yeah, and so just as a quick follow-up, so any of those examples I think would work for this question, but maybe the temperature sensitive or the temperature reactive one, just a quick one. So maybe weave in, how, from the current state of the art or the current approaches that are being utilized, how would that approach be beneficial to, for sake of argument, someone who's dealing with cancer what's the benefit that the patient
Right,
is
that's the
getting?
benefit. Yeah, of course. So I mean, I think most of us know that current treatment options for cancer patients, for example, have a lot of limitations. We are familiar with things like chemotherapy or radiation therapy or even surgery. And while those can be effective, we also know that they can do a lot of harm to the patient, right? Chemotherapy, for example, can lead to severe side effects because of its toxicity on healthy tissue. And so what we're trying to develop is some things that can be much more specific, that hopefully can only act at the site where they are needed, therefore leaving the rest of the body untouched. So we're definitely trying to improve not just the efficacy of it, but also the specificity so that the patient can have a better quality of life. And that's enabled by the materials that we developed.
Very good. Good, thanks. Dami, welcome.
Thank you.
So, we're going to play a little tennis match here. We'll go back and forth with Betancourt.
Yeah,
so,
yeah.
So on a similar vein, related type question. So if you can, give the audience kind of a background about you, where you're from, how you know, what led you here to Texas State, and then just to set the stage a little bit, I'll probably use that to lead into maybe some more specific personal questions about Texas State, but just background first. So what got you here into the MSEC, Material Science Engineering and Commercialization Program, PhD program at Texas State?
Thank you, Dr. Piner. Prior to attending Texas State, I actually was at Lamar University getting my master's degree. And while I was actually there, I, for the first time, actually got introduced into the concept of entrepreneurship. And prior to coming to Lamar, I just concluded my undergrad degree in Nigeria in chemical engineering as well. So I got involved with entrepreneurship, and I actually met a professor from Texas State, and that's how I knew about Texas State University. And during that competition, I did some very basic research into sensors and its application for everyday human life. And I guess during my time at Lamar, I got involved with a startup. A couple of friends of mine actually started a company, and I was helping develop the product. And one of the things I found out was I had a really limited understanding as to how to make the product work better. So the product was to just generate water from the atmosphere. And yes, just like what the big idea focuses on, we're actually making this possible by altering the characteristics of materials in order to make water generation possible. But I found that I had a really limited understanding as to how to make the materials act the way I wanted it to act in order to get more water. So I thought to myself, I should probably try to increase my knowledge on this particular area of materials characterization, or just changing the ways materials behave. So I thought about actually coming for a PhD program. And because I'd already met with a professor from Texas State University, he had told me about the uniqueness of the MSEC program. So it was a PhD program that also gave you the opportunity to delve into entrepreneurship. So I was like, yeah, this is a no-brainer. I already have some experience, so I'll just just continue with that. So I came in here, and I was able to meet with the department chair of the program. And from her, I got introduced to Dr. Betancourt. So I actually have two advisors. And I remember I had my conversation with Dr. Betancourt because prior to coming, I actually wanted to work on sensors for sleep apnea, because there's like a personal motivation with that. So I felt, oh yeah, I'll just work on sleep apnea. And I had this really bogus idea on how the product was going to work. And then, you know, after talking with her, I saw what was achievable and what we needed to figure out, hence my dissertation. And that's how I found myself here, pretty much.
Okay, excellent. So maybe just, you know, I'm trying to put myself in the shoes of an audience member who's maybe not that familiar with graduate school, or maybe even specifically the types of research that we're talking about here. So just, you know, to help put some color to this conversation, you know, just maybe walk the audience through, you know, what it's like from your perspective to do the research that you're doing. Maybe speak a little bit to it to the extent that, you know, you can relate it to the audience as well. But, you know, what's kind of like the day-to-day life of a graduate student in general, but because I think our programs are very,
Okay.
very analogous, but more specifically, obviously, at Texas State as well.
Okay. So that's actually a very good question. So for me, because I came in more or less with an end goal in mind, I knew that I was trying to make a certain type of, I was trying to do research in a certain area that was going to be applicable for, let's say, commercialization. So in my case, I'm working on biosensors for detecting cancer. So the first thing we had to figure out was how I wanted to go about doing that. And there are lots of ways that you can go about doing this. And Dr. Betancourt has shared some of that. So particularly I was trying to look for non-invasive ways to do that. So that meant trying to find the least possible way or the least invasive way to actually get those samples from the human body and then analyze the samples. So most times day-to-day is trying to figure out how to first make that material and then try to modify the material to be able to actually determine the particular biomolecule or the material in the body that can actually tell you if you have the specific disease, and then try to see if that's successful. And most times, more often than not, it's not going to work out the first time. So it's like you solve this problem and then you find another problem and you find out, okay, I made it identify this material. But now what I'm seeing is I cannot really make sense of the data, or I cannot actually say if I identify the data, and then I have to go back and figure out what else to fix. So you just keep having more. So with each solution you get, you have new problems to kind of figure out. So most times I find myself having conversations with both advisors and how to solve these problems, either at the same time or just doing it one by one. So it's like you're trying to schedule, because you have, for example, you could have a case where you have to run multiple experiments to figure out if a step is working. So in the process of that, the material that you've made might just run out, and you might be thinking, okay, I need to make more of this. And then there's the logistics to that. How long is it going to take before you get all the materials that you need to run the experiment? Okay, in your schedule, because you have other commitments, how can you make time out for that? Another thing that also I have to figure out is I find issues with finding areas that I'm not so good myself. So I need to find someone else to work with to help me with that. So I need to work with other people who might have expertise in that area and find times in their schedule to partner with them in order to solve my problem. So that's kind of like what my day-to-day life is like, pretty much, as a scholar.
Excellent. Yeah, that's awesome. So I appreciate the insight. So segueing a little bit, so Dr. Betancourt, we've talked a lot about a variety of activities, very advanced science, in particular, just to use a general term, talking about students and doing these various types of research and experimental activities, which brings into play the necessity of funding to enable all of these things that we're discussing here. So either specifically or generally, however you want to approach it, just if you can, just give the audience from the advisor, from the research advisor's perspective, what sort of funding are we looking at here in terms of enabling your types of activities? Where does it come from? What's the process for achieving it? Where does it go in terms of rough numbers or percentages maybe in terms of laboratory type support, student support, things of that nature?
Absolutely. So, of course, to be able to conduct any of the research that we discuss, we need funding. That funding typically is acquired by the principal investigator, who is the advisor, and that's typically done through a proposal or grant writing, basically proposing a technical idea to a federal agency, perhaps, or a private agency. And the idea has to be, there has to be a good motivation for it. There has to be good science behind it, behind the solution that you're proposing. And if you're able to convince the agency, then you might get some funding. That funding, depending on the type of funding, it could be maybe for a year for maybe a small project, or it could be something multi-year for a larger project. And typically that funding is going to cover the students or the personnel that is going to be involved in that. And that's actually a big percentage of where the funding goes. And I'll get into more details in a little bit. But it also funds supplies that are required, all of the reagents, chemicals, cells, equipment that you might need to develop, characterize, and evaluate the materials. And then also access to facilities, for example, large equipment that we don't have in every single lab, but that is accessible at core facilities, either at the university or outside of the university, and that we need to pay in order to get access to. Things like electron microscopes or fluorescence microscopes that are more sensitive than what we have in the lab. And so it pays for that as well. Coming back to the personnel, typically funding for a doctoral student in the material science program will be something in the range of 40,000, if I am correct, per year. And that's basically just living expenses for the student and the money that they need to pay the tuition for themselves. And then we also involve in the research not only graduate students, not only students from the MSec or materials program, but also master students from our chemistry, biochemistry, and biology programs, for example, for my research. And we also involve undergraduate students. And all of them ideally are getting some kind of stipend to be able to support them for the time that they invest into this work. For undergraduate students, that might typically be just an hourly rate, or maybe like a summer stipend if they're going to be working full-time. And then for master students, ideally a stipend for the semester. Also, I'm not sure exactly the rates right now, so I don't want to provide a number that might be wrong, but it's on the order of a couple of 10,000s as well per year. What else can I say? The funding, again, is something that the principal investigators need to continuously apply for, because as I mentioned, a lot of times it's for a short period of time and then that runs out and we have to, make sure that more is available to us. There are also internal, Texas State University resources that can help out a little bit. And that's definitely helpful, if you're trying to start a new project for which you need preliminary data, for example. So having a small pot of money that to enable you to obtain the supplies to gather that preliminary data, that would be very helpful to be able to support a larger grant application. So yeah. Did that answer the question more or less?
Yeah, very good. Yeah, just one quick follow-up. So again, I know in my area there's a significant degree of competitiveness.
Oh, yes.
When it comes to achieving these sorts of funds. It's not like, okay, well, I'm gonna write a proposal and wait 3 or 4 months and then the award's gonna come in and I can count on it. So maybe from your perspective, just to again help everyone understand, what's the competitive environment like when it comes to achieving success in terms of getting these awards, and then also as a follow-up, it's the money comes in or the funds come in, and then there's expectations on a lot of those funds in terms of what you have to do from the technical side, deliverables, I often call them, depending on the funding agency, that what are they expecting in return? But I guess more critically, the competitive aspect of it.
Of course. So yeah, as you mentioned, basically, the environment is very competitive. Maybe the rate of success might be in the 5 to 10% of all of the applications that of all of the applications that are submitted countrywide to one solicitation, 5% might be awarded. So it's very competitive, especially when we're competing against very large universities or maybe like cancer centers for the type of research that I do. It is very difficult to obtain the funding for sure. you know, at this, another issue is the extent of the work that can be done at a university like Texas State, where we don't have a hospital associated, for example. We need to definitely establish collaborations to be able to make us more, you know, appear better, having better resources to be able to compete against some of those larger universities. So it is very competitive. Now, once we actually get the funding, we also have to demonstrate that we are being able to do what we propose to do and that we're doing it well, that we have sufficient results to make it worth it for the agency to fund us again, whether that's just a continuation of the same grant, which some agencies allow, or whether we have to compete all over again against, you know, the same groups again. So it is a very competitive environment. You know, each principal investigator or each professor has to submit in the order of 5 to 15 grant applications per year to maybe be able to get one or something like that. So it is quite difficult. Again, you're competing against people that are very established, that have large groups with a number of postdoctoral researchers, which is, you know, it's just difficult for us to compete against. So we definitely can use more help.
So along that same line, Dami, so as a graduate student, a PhD candidate or case, can you give everyone a feel for the importance of that funding that's provided to you? And just, so Dr. Betancourt mentioned stipend, and so there are specific terms. I don't know which source you tap into, or maybe most of these, but you're talking scholarships, fellowships, assistantships, and then there's different subcategories under those. But setting that aside, the more pertinent question, I think, is, as a graduate student, someone who's looking to do the very advanced research and to ask and answer a question that's never been asked or answered before. It's just cutting edge research we're talking about here. It's not something to look up in a book and your results are correct or incorrect, or on the right track or not. So having that funding, what does that mean to you as a graduate student?
So for me as a graduate student, having that funding, honestly, I think it actually can tell if it actually can tell if your results or whatever you have done research, it kind of helps you with, I guess I can say it helps you with the speed to which you're able to publish in some situations, sometimes. I would explain. So one of the materials that I actually use for my research, I typically have to like synthesize it in one of the labs that I work in, and then I apply it in the other lab. So ideally, if I wanted to focus more on the application portion of it, which is more important, trying to figure out how to make it work, you would want to purchase the thing that I'm synthesizing. But typically, if you were to purchase that, it could cost a couple of thousands to get the quantity that I can use over and over again without worrying about running out of the material on time. So typically, if you have more funding, it could reduce the amount of time it takes in doing some repetitive work and actually focusing on what is truly important, which is figuring out the hows and the whys and trying to make that application ready quick enough. And also to add to that, I could say, for example, because sometimes I might have an idea and someone else, a graduate student, is also working on something similar in another school. But sometimes the availability of funding might actually be the difference to who's able to publish that result first. Because sometimes when you publish that, if you're the first person that publish it, you have more of an impact because your result comes out first. People recognize you for that. But if you're having to think about the funding and work around your budget and try to get it done, you kind of take longer periods of time, and you're just one of the other people who's just doing it right after that person has published it. For me, that's what I've seen. And I think that's one of the major things in my line of research that funding plays in.
Yeah, excellent, okay. So switching gears a little bit, but I'm gonna, let's bring into play now some of the key areas that, or the connections, I should say, in what we've been discussing, your all's areas of research, advising, student perspectives with this concept of materials of intelligence. And so there are several aspects that that's, in fact, for the audience, that's available on the website. If you're curious, I would encourage you to go there and look into some of the details, but I think one of the key aspects that's of particular importance to this discussion is just to read one of them. So what we're talking about within materials intelligence, it encompasses advancing sensor technology and or materials for better sensing capabilities in their applications. So kind of a general phrase, I think, is that's applicable to what we've been discussing here. But then actually building off of something that both of you said during your responses earlier, and that is one of the key objectives within materials with intelligence is to establish a platform, maybe a center, an institute, the terminology is whatever it needs to be at the end of the day, but more critically to enable and engage collaborative research and development at Texas State. The key word there is collaboration. And so one of the ideas behind this, one of the big concepts again, is to, within the university, a setting, whatever that may be, that would foster collaborations, both at, and I'll start with you, Dr. Betancourt. So from the research advisor / principal investigator perspective, if you can speak to the advantages that you could envision by making it easier to establish, first of all, internal collaborations with you and other advisors, and maybe perhaps at another level connected to other types of students, what that would mean to you, and then also, if you can, how could that expand from this, from the research that you're currently doing? How could that broaden it? How could that make it bigger than what it is? What would be the advantages of establishing, enabling those those collaborations through a materials with intelligence sort of framework?
Right. So for all of the materials that I develop, collaborations are critical because, as you mentioned, the interdisciplinary nature of them. Being a biomaterial, for my case, we need the biology expertise, we need the chemistry expertise. Eventually, like for a biosensor, we need expertise from engineering that are going to help us have a device that actually can be used. So collaboration is critical, and having some kind of structure or infrastructure to help us build and establish and maintain those collaborations, that could be quite helpful. I could envision many forms in which that could work, but it could help to establish teams maybe at the beginning to form new projects that might not have come about had we not actually sat down and talked about our expertise, for example. It could be helping us to recruit students that could help us, take a project from an idea to an actual deliverable that could work between the different groups. It could provide, funding for some, again, for some new projects so that we can gather some preliminary data to then be able to seek further funding. So there could be a lot of ways in which a center or some kind of infrastructure like this could help us. But it would definitely enable new projects that would not come about had those discussions, those collaborations not come about. So they are critical. They could basically expand the range of things that we could do. And we've already seen that here, with the collaborations that we're already doing. As Dami mentioned, his project, for example, is a collaboration between Dr. Jennifer Irvin and myself. She's an organic chemist, and so she's able to help us with all of the synthesis and some of the materials development, while I'm able to apply the biomedical aspect to that. And so again, establishing those collaborations enables us to have projects that we couldn't have done otherwise. Like by myself, I would not have been able to develop those monomers that are required, or monomers or chemicals that are required to be able to make the materials that we are making with Dami. So that is very important. I could envision something like that, definitely expanding the research, not just for myself, but for many of the faculty that are materials related at the university. There's a lot of people in the Department of Chemistry that can do interesting synthetic chemistry. Some of them develop molecules that are responsive to to stimuli, to things like heat or light or mechanical stresses. And those could be utilized to build materials that are intelligent in themselves. And then again, partnering with engineering to be able to actually use that to develop a product, a device, or something like that that can be helpful to society. That's critical.
Yeah, so Dami, along those same lines as a graduate student, so you've already mentioned the collaborations that you've had to establish, but maybe helping folks understand what are some of the benefits, or maybe what's the criticality beyond just the simple, but maybe just beyond the concept of a benefit, but what sorts of things are you relying on other people to do, and having those sorts of collaborative, having an environment that's collaborative, that's key to you. And as you mentioned before, maybe if you can, or if you like, if you want to extend that same question into your prior life, I'll call it entrepreneurship, or your small company activities. And I'm assuming in that environment that collaboration, working with others, was absolutely critical. And just to paint a bigger picture, one of the things I've seen, at least in the area that I work in, and I'm assuming it's the same in yours, correct me if I'm wrong, but the types of problems that we're dealing with today, it's nearly impossible for an individual to have the resources and all of the necessary expertise to properly tackle it and make headway on it. It really almost necessitates these days a team effort. And so, with that as kind of the stage, if you can speak to key, specifics in terms of the collaborations that you do, how they're beneficial to you, either again as a graduate student, if you want to go back in time a little bit to your company.
Okay. For me, I guess collaboration is important because what it actually helps you do is to focus on what the end user is really important, what the end user actually wants. Because all of this research that we do, all this multiple projects that we have running on campus, at some point to actually bring the value out of it, you actually want to have people who have specific expertise come together and combine all those multiple projects and see how it can be applied to a real life situation. So I can use my research as an example. So I'm currently working on a biosensor, but what I'm doing right now is the fundamental research and trying to make sure that this concept can actually work. Now, the next phase would be to collaborate with someone in the manufacturing department to help me make a smaller device that could help effect a change to the materials that I'm already testing right now. The next thing that's going to be important after that is to actually collaborate with someone in the computer science department who can help me make sense of the interactions that's going on with the material and that device that the manufacturer has built for me. And the computer science department is going to be able to make the software end of it so that a medical doctor can see that data and say, okay, I can see this. So this means that this patient's cancer is either progressing positively or negatively. And that in turn helps the patient by making sure that they don't have to be exposed to more X-ray radiations. So this is the big picture, and this is sort of the future of why collaboration is important. And if we don't see it that way, then an actual product in its sense cannot be made, which for me is really important. The reason I'm doing my research is because I want to actually, at the end of the day, affect lives at some point. In the past, while I worked in the atmospheric water generator company, I worked with chemical engineers, I worked with people in computer science, also doing this kind of stuff. So I have an idea of what an actual company or team is comprised of to actually make something that would be, at the end of the day, important to an end user, because that's what I believe all this research should be all about.
Great. And I'm kind of doing this off the cuff, I guess, so for the audience, but we haven't rehearsed any of this. So something that's really got me intrigued here, Dami, is within the company that you started. So it sounds like if you can't speak too much about it, that's fine. I understand there may be some confidentiality concerns, so don't let me, I'm not needing to step on toes here. But so maybe in a general sense, it sounds like that was very formative in terms of directing you to to the graduate studies that you're doing today.
Yes.
I guess how much of a future do you see in terms of I don't know how far you got with that in terms of the technology, or if it was the terminology that I typically use would be like, it sounds like you were making a prototype. You would make a prototype to show proof of principle, proof of concept, and assuming success there, then it goes into another phase, and maybe after that phase, there's a finding at some point into the production phase. You can actually release it to and make it available to the general population. Let me ask it more generally, because I'm afraid I'm going to step on toes here. So, where do you see yourself in a few more years with a PhD degree in hand at Texas State University? Go Bobcats. And how are you going to be using this? And then I'll just go ahead and set the stage. I'm going to relate this back to materials with intelligence at some point as well, but just in general, without getting into that context.
Okay.
Where are you going with this?
So for me, the end goal has been to be able to commercialize my research. So right now, I've actually been first improving my knowledge on the fundamental science as to how the materials work and how I can apply those materials to solve real human problems. And the next phase for me will be making useful contacts. And this I can do from collaborating with different people, because I need to find the individual expertise needed to actually make a successful company work. I guess the next thing I can do after that is figure out exactly, because that's also another thing that I have planning in the works. Once I'm able to find out what actually works in the technology, is now to actually go out and talk to the end users. And thankfully, Texas State actually has another collaborative effort with the National I-Corps, where you have the opportunity to actually work with group of mentors to be able to reach out to end users and ask them, what are the problems they're facing, and then see how that technology can be fine-tuned to solve real-life problems. So at that point, for a fact that if you can commercialize this technology, you could actually start a company from it, and reduces the chances of failure of the company. So I see myself being able to actually make sure that the fundamental science works. And next is to answer the problems, or answer the question of what specific problems do I see doctors having with the current solutions of biosensors that they have. And once I have that, I'm geared or armed with the expertise and networks that I've made, I could start a company in the future that actually focuses on that specific problems, and hopefully be successful doing that.
Yeah, and so just one quick follow-up. So it sounds like you're ahead of the game, I would say, well, for two reasons. To give a pat on the back to our material science engineering commercialization program. So you've already commented on the entrepreneurial aspects of the PhD program that we have here within engineering at Texas State and science at Texas State University. You also have another benefit in the sense that you've gone through at least one iteration of endeavoring to do a startup, right? Or to get an idea from the paper into the actual space. So maybe with that as the segue, the question would be, have you thought about how you would go about taking, let's assume success, to take the idea, the research that you're currently doing, and actually, like the logistics, the nuts and bolts of taking that and then commercializing it. Without getting into too many specifics, but maybe more importantly, what I'm thinking along the lines of would be, okay, here at Texas State, we've got certain capabilities, for example, Star Park, our incubation, our innovation incubator site, and some other resources. So with those kinds of opportunities in mind, what would the nuts and bolts be like for you personally to take that transition that you're hoping to take?
Okay, so the first step would be first to find the solution to the question of how to actually successfully detect the cancer biomarkers in this case. And once we're able to do that, the next step will be, well, because it's a university funded research, you'll file a patent for that. The next thing I would personally do would be to actually go through a series of customer discovery with this technology. And once I'm able to identify the actual problems or the pain points of people who could use these technologies that speak into current cancer patients, and also speak into the doctors who have to also see those patients. The next one will be to actually see, since I have the information of what the problems are and already have an established technology, I can speak with the university and find a licensing deal to actually license this technology from the university. And the next step will be to actually either apply for an SBIR grant, and the university has resources that could help with that. I think they have some collaborations with, I think it's the SBA, if I'm correct, and I'll speak with them. And the new ventures, they also have some competitions that can help get some initial non-diluted funding. And also they can give us space, office space and research space. So ideally a startup, one of the things that probably hinders their progress is not having that much money to start in the first place. And that's where I feel having a good collaboration with Texas State, having the new venture, the startups, the Star Park, I guess, having the Star Park, you could have, I'd say, better deals because we're affiliated with Texas State universities, and that can help reduce the initial cost that it might, take to actually go out there in the world and do this on my own. So since it's a university funded research and it's also supported by university, I already kind of have a little bit of a cushion to help see this project actually grow into an actual company. So once I'm in there, I could tap into other resources, tap into the mentors that they have over there, and try to find the next direction and as to how to either engineer that final design, and then after that, trying to see who would be willing to test this out there and just kind of go from there.
That's great to hear, because that's a great segue into, as we're checking the time here, getting ready to, getting very close to having to wrap up. But so earlier when I was discussing getting that brief, really which materials with intelligence encompasses, and then as we discussed collaboration and internally collaborating, I will also note that at another level of that collaboration that I'm envisioning within this umbrella of materials with intelligence, whether it's a center or a site, whatever it may be, down the road as the funding for it materializes, is to also enable the collaborations at the level of the entrepreneur that you're describing here. And so to facilitate those sorts of connections, to make it, to help facilitate, either directly facilitating them, providing resources to our students directly through the funding, or or of course through seed funding, as you mentioned, Dr. Betancourt, for the research that's actually happening here. But then, yeah, that transition period, to be there as a resource for students like you who need it and can leverage it to do, or to help you do all those things that you're, sound like you're chomping at the bit, ready to jump in and go for it. So that's great. Well, I appreciate so I hate to just wrap, but Dr. Betancourt, Tania, I'll kind of open it up. Anything that we haven't touched on that you would like to make mention of, or any other comments you'd like to make that you feel like you haven't had a chance to lead into yet?
Maybe one more thing that I wanted to mention is that in all of this research, the research is hugely important, but another thing that we do is also the education of the students, right? And obviously we have gotten the perspective from Dami, from a doctoral student whose main part of the studies is the research. But at the same time, again, as I mentioned, we do involve undergraduate students and master students in the research, and that's a hugely important part of what we do. Getting students exposed to science, the real science, not what's written in the books, but actually getting them to see that science is not a linear process, but instead an iterative process, like Dami mentioned. We're always troubleshooting, trying to investigate what happened, trying to fix what didn't work, trying to test our hypothesis, and getting students involved in that early is a huge, it can make a huge impact in student retention and their success, especially students from underrepresented minorities who might not have that, access to that information and that experience in their households necessarily. So that's something that I just wanted to bring up, that's an important part of what we do here.
Yeah, I would say, the way I would state it, the scientific method is simple to state, but profoundly challenging to implement.
Yes. Hence the word research, right? Search again and again. And
That's a good word. That's a good way.
you learn a lot along the process. You know, it's about the process, not the end goal.
Tommy, anything,
Yes.
any last minute, any closing, not to put you on the spot, but we've covered a lot of ground. I appreciate the time, but yeah, anything we didn't
Oh yeah,
touch on?
sure. I mean, I think for me, just looking back as to how far I have grown from when I started my first conversations with Dr. Betancourt. Like the things we spoke about was so funny, and I just look at myself and I'm just laughing because I'm like, I literally came in with a hypothesis that was totally off of what was achievable, and just seeing the journey and seeing how far I've grown from that to now is just interesting. And I can literally say I was pretty much, I'm trying to use this word, but I guess it was possible because I was trained by the whole community. So I wasn't just able to reach this particular level because I just had only Dr. Betancourt. It's a combination of interaction with different professors, different students, even some people from outside the university that had some opportunity to come talk to us or take us into their own world. So that keeping the collaboration open, whatever it takes resources wise, to just have that open conversation, have that cross interaction is really important in making sure that you actually value the quality of education you get from Texas State. So
that's a great perspective to end with. That's awesome. Yeah. So, Tommy, Dr. Betancourt, thank you very much. Appreciate the time y'all have given to the Church of Intelligence, big ideas, and supporting this week's efforts. And best of luck to you in your studies.
Thank you.
And your advising. We didn't touch on that, some of the ins and outs of the advising role, but that's okay. We can.
That's another topic.
Topic for another day. Yeah. So, okay. So, Nicole, we can sign off, but thank you all again. And I'll see you around campus.
All right. Thank you very much.
Thank you.
Thank you.